Hi there! In this R Labs lesson, we will be talking about representing population dynamics with difference equations. In this particular video, we'll discuss the basics of difference equations using some simple tools such as for loops and functions. If you don't know much about for loops and functions, feel free to check out our other lessons on these topics. In the accompanying application video, we'll discuss a special case of representing population dynamics with difference equations, namely representing deterministic chaos and generating a bifurcation diagram. So first we need to understand that population dynamics considers how populations change in size or composition over time. So here, for example, we have the density changes of a single species, a field vole, over time. And over here we can see the classic multiple species example, where we have the related changes in the abundance of both lynx and hares. Now, in terms of representing population dynamics, we can use difference equations for dynamics in which major population changes occur in discrete time intervals, or we can use differential equations for continuous rates of population change. And this second option is typically seen as being more accurate, but in this lesson we're going to focus on representing single species discrete time dynamics with difference equations. So the first discrete time dynamical model that we'll look at is for exponential growth, meaning that populations are assumed to be capable of growing indefinitely. Now, one way to represent exponential growth is using a difference equation to tell us the new population as a function of the old population and the per capita birth rate and death rate between time intervals. Now, I've included the full derivation here for your interest, but the simplified equation is right here. The new population size is equal to this lambda term multiplied by the old population size, and so the lambda term accounts for births and deaths in the population. Now, in terms of solving this discrete time growth difference equation, we have two options. First, we can solve the equation numerically by simulation. In R, we use a for loop to do so, and we also have the option of using functions. So let's just switch to RStudio for a minute and examine how this would be done. Okay, so we'll keep the equation on the screen here just as a reference while we solve it numerically. So we know that we'll be getting new population sizes as an output, and we're going to want to store these output values in a vector. In this example, let's say that we want to investigate the population size at 10 discrete times. So we'll make a variable called generations and assign it a value of 10. Then we use the numeric function to create an empty vector with a length specified by generations, so the length 10. Okay, now the next term in the equation is lambda. In this example, let's call the variable lambda, and we'll give it a value of 2.1. And now finally, we need an initial population size. In this example, let's use a population size of 3. We specify the initial population size by indexing the n vector that we just created. So we say the first element of the n vector is equal to 3. And now we use our difference equation in conjunction with a for loop to fill in the other vector values. So here's the for loop that we'll use. Again, if you want to understand this loop a little bit more, check out our lesson devoted just to for loops. But basically, this for loop is setting an index variable called t equal to the numbers 1 to generations minus 1, which is 1 to 9. And then while looping through all of these t values in turn, the t plus 1th element of the n vector is being assigned the value of lambda times the tth element of the n vector. So this part of the for loop here is essentially the difference equation. Now note that we only have t set to equal 1 to 9 instead of 1 to 10 because altogether we want 10 generations. So when t is set to equal 9, we can substitute 9 in for t here, and obviously since 9 plus 1 is 10, then the 10th element will be generated in the n vector, and therefore there is no need to set t equal to 10 to generate more values. Since we have executed the loop, we can now examine the n vector, and we can see that our loop has indeed worked. We have 10 values in our vector. And just to visualize the data, we can plot out the time versus the population size. Again, here the x-axis is going to range from 0 to generations minus 1, so from 0 to 9, because we want 10 generations all together, and we're calling the initial generation 0 instead of 1. And here is the resulting plot. Now, if we wanted to experiment with multiple values of lambda and 0 in generations, perhaps the easiest way would be to create a function. If you don't know much about creating functions in R, you might be interested in our lesson devoted to functions. So here's the function that we will use. I've called the function popGrowth, and the input values are lambda and 0, the initial population size, and the number of generations that you wish to investigate. Then within the function, we have specified an empty n vector that will have the number of elements specified by the generations argument all together, including the n0, which is the first element of the vector. Next, we have specified the for loop, and we will return the n vector. And now we can call up the function specifying the lambda, the initial population size, and the maximum number of generations. I've just stored this in a vector called output. And then we can view the vector and plot it out like before. And here's the resulting graph. Okay, so the second way to solve this discrete time growth equation is explicitly, mathematically. Basically, it is possible to derive a formal relationship between population size and time. Again, all you really need to know is this equation here. It states that the new population size at time interval t is equal to lambda to the power of t times the initial population size at time 0. But if you're not convinced or you're just curious, you can look above here and figure out why this equation works. So let's just quickly move back to RStudio again and put this explicit solution to work. So here's the equation we're working with this time. Again, we'll just keep this on screen for reference. So first we need a lambda term. We'll call it lambda, and we'll stick to the same example as before and give it a value of 2.1. And then the next term we need to define is t, time. So as in the last example, let's examine 10 different generations. If we define the initial population size as time equals 0, then 10 generations would be 0 to 9. Next, we define the initial population size n0, giving it a value of 3. And finally, we just need to specify the actual equation. So nt, the new population size, gets lambda to the power of t times n0, the initial population size. And since t is a vector with more than one element, the output nt will also be vectorized, and then the single lambda and n0 values will be recycled for the calculation of each output value. And again, we can view the output and plot out the relationship. Now in reality, population sizes don't tend to grow indefinitely. We often see density-dependent growth or logistic growth. As seen in these examples, we initially have exponential growth, but then there is an upper limit, a carrying capacity k, when the population levels off and can't grow any further. Now the difference equation for the discrete time logistic is shown here. This is the exponential growth equation from before, and this is the added portion that limits the growth. You can see that we've just introduced the carrying capacity term k. And the way to solve this discrete time logistic is numerically by simulation using the for loop and functions again. So here's the discrete time logistic equation. And here's the function that we will use to represent it. So I've called the function dlogistic. The inputs are k, r, and 0, and then the maximum number of generations that you wish to investigate. And again, we have a vector called n, which will contain the number of elements specified by the generations argument altogether, including the first element, which is set to equal n0. Then we have a for loop to fill the rest of the vector. So we can create a vector called output, and then we can call up the function, inputting the various values as arguments. And finally, we can plot out the results. Now, just as a side note, there are also many other discrete time single species population models out there aside from the two that we covered today. Thanks for listening to this RLabs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.